So talking just a couple specific theorems today, which are probably kind of obvious to you once we start thinking about them, but you can use them again for some more applications of some functions, basically. Okay. One of the theorems is Rolle's theorem. Let f be a continuous function. Okay, so we got a continuous function. There's no breaks in it. There's no asymptotes. Okay, it's a continuous function. Okay, on a closed interval, on any closed interval. Okay, and between the outsides, between a and b, all right, it's differentiable, meaning there are no sharp points. Okay, you can find the derivative on any value between a and b. Okay, so you got to kind of have that in mind. If f of a equals f of b, okay, so here's kind of that general idea then. So here's my a value, so we'll call this f of a right there, and then here's my b value. It says they got to be equal, so in other words they'd have to be the same, have the same y value, right? So if f of a equals this much and f of b equals the same thing, and I got a continuous function, okay, I'll just draw any continuous function. Wouldn't it make sense that at some point between a and b, the derivative would have to equal 0? Guaranteed, right? Even if I had a horizontal line, then everywhere the derivative equals 0. That's Rolle's theorem. Okay, if f of a is equal to f of b, then there exists a c value in the interval ab such that f prime of c equals 0.
Is that f of c on the graph? Or is that f of
That's an a. Yeah.
Is that f prime?
Right here, yes.
Alright.
Yep. So, that's Rolle's theorem. If the values, I'll even shorten this up. If the y values at the two endpoints are the same, somewhere between those two endpoints the derivative has to equal 0. As long as you have a continuous function that's differentiable everywhere. Okay. Where essentially could that be applied? Well, let's say you knew the zeros of a function. Okay. If some function has, and you know where a couple of the zeros are, if you know you have a 0 here and you have a 0 here, would it make sense that then there probably, unless it's a horizontal line, there would probably have to be a maximum or minimum between those two x values? Because somewhere it's got to, the derivative has to equal 0 between those two. So it's just kind of a conclusion you can make. They call it Rolle's theorem. Okay, but basically it's just saying, okay, at some point between a and b, my rate of change is 0. Could be multiple points. Could just be one. In my drawing, there would have been 2. Okay? That's Rolle's theorem. Everybody got that? Quick application problem, something similar you might have to do. First of all, let's find the x-intercepts. I'm just following the book's example here. Find the x-intercepts of f of x equals x squared minus 3x plus 2. How do you find x-intercepts? Plug in 0 for y and solve for x. Okay? So 0 equals x squared minus 3x plus 2. How do you solve that?
Factor.
Hope to God it's factorable, so you don't have to use the quadratic formula. X minus 2, x minus 1, right? So therefore x equals 2 and x equals 1. And then, now that we know the x-intercepts, I want you to show me that between 1 and 2, there exists a point where f prime of c equals 0. Or in other words, show me there exists a point somewhere between 1 and 2 that the derivative would equal 0.
Well, couldn't you just basically say either it's going from point to point where it's 0, or if it changes either direction, then it would have to change direction, at which point it would have to have a place where it bottoms out or has to equal 0.
Yeah, but I want you to show me where that point
Okay.
is. Yeah, but yes. So what are we going to do? Find the derivative, set it equal to 0. Hopefully it's somewhere between 1 and 2, right? If you know parabolas, it's going to be right in between them because parabolas are symmetric. F prime of x would be
2x minus 3.
2x minus 3.
0 equals.
0 equals 2x minus 3. X equals, surprise, 3 halves.
So
1
1
1/2. Okay. So there exists a point such where f prime of c would equal 0. So in other words, we know that f prime of 3 halves equals 0. If you wanted to find the coordinate that goes with it, plug it into the original to see what the y value is to go with that coordinate, to go with that x value of the coordinate. Okay, so that's Rolle's theorem. Really pretty simple. I don't know that we use it a ton, but I want to make sure you're aware of it. We don't use it a lot going forward. It is a test question, okay, for you, but we don't use it a lot in calculus anyway.
But it's kind of neat.
Yeah, just kind of because of all the things that we know, this is a theorem that can be proven true.
Now, wouldn't the inverse of it not be true? Like, couldn't you have an example where it doesn't end up the same, but it still has something in between?
Oh yeah, true. Yeah, you couldn't say that because if they had different values or whatever. But speaking of that, that's kind of actually there's a different theorem that when they do have different values.
What happens if that x value doesn't fall between the two
Probably did something wrong.
things?
Because yeah, no.
Like, if that was a possibility or not.
As if you know, because would you agree that f of 2 equals 0? Okay, because we know we found the zeros when we did this factoring. We found the zeros, and we know that f of 1 equals 0. So they're both equal to the same amount. You know, it's kind of like having this picture right here. And would you agree that this is a continuous function, x squared minus 3x plus 2? Most polynomials are going to be nice continuous functions.
As long as
Okay?
it's not over something.
Yep, as long as it's not a rational function, absolutely. So, yeah, if you don't find a point in between those two, check your derivative, make sure you have it right.
Because, like, it's either a straight line between it, which means it would all be 0, or if it moves up or down, it would have to change direction, thus making it so that it would eventually have to bottom out or top out.
All right, next one, second theorem. Okay, let's see.
Excuse you.
Okay, so Now I got this closed interval AB, and the value of f of A does not equal the value of f of B. Okay. If I were to draw a line through those two endpoints, what would the slope of that line represent?
The average
The average what?
speed or rate of change?
Average rate of change. Yep, that would represent the average rate of change. Okay, so if this was, distance. Okay, use distance and time. Well, this is if it started here and ended here. This was our average. This was if we were to do it at the same increased rate the entire time. This is what our average would have been. Okay? Doesn't mean that's how fast you went the entire time. Obviously not. Okay? But that would be our average rate of change. Would you agree that if this slope represents our average rate of change, somewhere between A and B, our instantaneous rate of change would have to be that same number?
What did you just say?
If this slope of this line represents our average rate of change, wouldn't there have to be some point between A and B where our instantaneous rate of change is exactly the same?
I'd say yes.
But what if, like, the graph was essentially a parabola that went up and connected to the other point where, like,
So if it did this.
oh, but then it would still have to at the start and end. Okay.
Yep, because
Never mind.
where's my...
Worst case scenario, start and end would have to equal.
Run.
You scared me there.
What was that waiting?
Beating the power of math into you.
Alright. So here's my average rate of change. There would still be a point, probably about right there,
I see.
where my instantaneous rate of change would match my average rate of change.
Yeah.
Yep.
Right?
That's what the book says.
Same thing on the blue one I drew. I'd say maybe about right there, but then I would say it does it again, potentially right about here, right? So there's a couple locations actually on that interval. Okay? That is called the mean value theorem. Mean, average. Okay? The mean value theorem. So I'm on page 174.
Long day.
Mean value theorem.
Bless you.
Thank you. Thank you.
Why did this guy name it after himself?
Maybe his name is me.
Not as
No, his name is Joseph Louis
Me.
Lagrange.
Lagrange.
Like that song.
Maybe he was a me.
MV.
MVT.
And me too.
It's like the
So again,
MBT.
F is continuous.
most value theorem.
Most valuable.
You gotta know it's continuous.
Otherwise, the exact point that you're looking for might possibly be not.
Correct. Yep.
It's not.
It is differentiable on the open interval. It's gotta be continuous on the closed interval, differentiable on the open interval. Okay. Basically, there exists a point C such that f prime of C equals the average rate of change. y2 minus y1 over x2 minus x1. That's all. That's the slope of the line right there. Okay, just a little different notation for you. y2 minus y1 over x2 minus x1 is what you remembered from algebra class. All right. But f of b minus f of a, those are the y values. You're subtracting those. Change in y divided by the change in x. Alright?
Oh, but
Okay, go to example 4, page 175. Kind of interesting example here.
why the heck is?
Get your dukes.
Oh, are those police cars?
We got 2 police cars.
What page?
Page 175.
Alright.
We got 2 police cars,
It's never a good situation.
5 miles apart. Okay? As the truck goes past the first patrol car, it was clocked going 55 miles per hour.
Smart.
And then 4 minutes later, at the second patrol car, it was clocked at 50 miles per hour.
What's the speed limit?
Interesting.
And the police cars going
But
the same
yet,
direction.
But
because
guess what?
it's 5 miles in 4 minutes,
They can give that guy a ticket.
because 5 miles, 4 minutes.
By the mean value theorem.
Huh.
What?
You'll see.
Can I read the
I
I know.
do see,
That's
but
how they do the white lines.
That's
on
how
there.
they do the white lines on the road, yep. Actually, when I was growing up, we were coming home from an Iowa game, and
There,
my
that's your
dad
problem.
got a speeding ticket. No cop ever saw us, but they said they had a patrol vehicle or helicopter up in the air, timing from white line to white line on the road, based on the amount of time it took. They guaranteed we were going this speed at some point. Gave us a ticket.
What? What's it time on here?
Good job, math.
Yeah, I know, it's great. Okay, so, first of all, it says let T equal time in hours when the truck passes the first patrol car. The time when the truck passes the second patrol car would be 1/15 of an hour, because 4 minutes, okay, you'll see there, time equals 4 minutes out of 60 in an hour, so 1/15 of an hour. It took 1/15 of an hour, or 4 minutes, for it to go from the first patrol car to the second.
okay.
Okay? Let's let S of t represent the distance in miles traveled by the truck. Okay?
Those aren't miles.
So S of t equals the distance traveled. Okay?
Which would equal 5 miles.
Well, we know that S of 0 was 0, right? At the moment he met the first patrol car, when time was 0, he's traveled 0 from the first patrol car. So S of 0 equals 0. Okay? And then S of 1/15 equals 5.
Okay.
Because 1/15 of an hour later, he had traveled 5 miles to meet up with that second patrol car. Okay? Graphically, I'll give you a little bit of a picture here. I got that written down. So this is time from the first patrol car, and this is distance.
Beast.
Okay? So, obviously, he passes the first patrol car, he hasn't traveled any distance from the first patrol car from the moment that he met it. Right?
Check.
Now, let's just for space-wise, we're going to say this was 1/15. 1/15 of an hour passed. Okay, 4 minutes have passed. 1/15 of an hour. Okay? And then traveled. Would have made more sense if I just had each box represent a minute, probably, huh?
Yeah, but
Eh.
You guys okay with this, or want me to change it?
You're fine.
whatever would make more sense.
I mean, it doesn't, just ignore the grid marks. Just
Okay.
go by what I'm labeling, okay? So, after 1/15 of an hour had passed, everybody understands how we got that 1/15 of an hour? The 4 minutes, 4/60. After 1/15 of an hour, okay, the truck had gotten 5 miles down the road. Okay? So, we don't know, okay, necessarily how it got from one place to the next as far as, you know, the rate of speed or anything.
But at the very least,
Oh.
at some point, the average is going to be
God.
that.
So this is his average rate of change, right? Okay, this would be the average rate of change. So, f of b minus f of a divided by b minus a will give us the slope of that line.
Okay.
So, this point is 1/15 comma 5, this one's 0, 0. So you do 5 minus 0
So 5.
over 1/15 minus 0.
So 1.
5 divided by
times
1/15, which is 75.
7.
Yeah. So his average would be 75 miles per hour.
He averaged
Wow.
75 miles per hour,
You look.
even though he probably had a radar detector, even though the moment.
Was Carmen driving this? Around that curve at Van Meter?
Yep.
Oh,
Sounds
I
I
exactly
love
like
it when
a
she
car
hears that on the
thing.
video, by the way.
Yeah.
You should have got a ticket, Carmen.
Come on.
So
Well, I
the
think she
average
probably
rate
did
of
look at
change
this truck.
says 75 miles per hour,
John could have been driving.
which actually tells you then
He was going faster.
he's
than
not going
that.
faster than
Because
75.
he started out at 55
Mhm.
and went to 50, so at some point he would have to go higher than that to make the average even higher.
Yes.
He was booking. What is he doing?
So
yeah, come on,
therefore,
Carmen.
because of the amount of time it took for him to cover that distance, his average rate of change was 75. Therefore, by the mean value theorem, okay, you know he had to at some point been going
Floored it.
75 miles per hour. You couldn't really give him a ticket for more than that. Okay, there's no way to prove how fast he was going at a given moment in time.
Maybe he just accelerated instantly.
But you're guaranteeing he was going 75 at one point in that time.
And even though technically it would be higher, you wouldn't know how much higher.
So
and
you couldn't
thus
give him a ticket
can't.
for anything higher. Yeah, there'd be no way to prove it. Alright? So, but mathematically, absolutely, you can give him a ticket for 75 because there's no way around it. The numbers don't lie. Alright?
That's what I like about numbers.
this math
Okay?
Numbers.
They probably have
obviously
computers
superior
that,
to
I'm gonna
humans.
get in
Oh,
trouble.
Daggett
I'm not even
knows.
gonna say, yes, I'm sure, the policemen are very smart and they know all this stuff.
Mr. Daggett.
Daggett does about hands.
So, there's a good application of your
Yeah.
mean value theorem. You won't always have story problems with it. Sometimes it'll just be guarantee that the slope of the average matches some instantaneous slope on the curve. Okay? I guess I can do a rough one real quick. Just kind of follow along. Well, this is what you'll end up doing. I won't do an actual problem. Okay? Here's what you'll end up doing. If I have, let's say this is some coordinate, I don't know, 2 comma 7, and this is some coordinate 8 comma 15, right? Just
Got it.
random. Okay? If you use your slope formula, so y2 minus y1 over x2 minus x1, you get 8 over 6, right?
Bingo.
15 minus 7 is 8, 8 minus 2 is 6, so slope equals
So we had to.
you need to figure out where on the curve the slope is 4/3. In order to do that, find the derivative and set it equal to what? 4/3. Yep. If you want to know where on this curve our slope is 4/3, just take your derivative, f prime of x,
And put
set it equal to 4/3, and then solve for x.
Wait, is that X double prime or?
No, that's,
Or F?
sorry. Yep, first derivative.
I was just.
Yep, I know. The lovely Mimeo. Okay, so that's the type of problem you'll be doing for the most
Got it.
part.
You're at 25 minutes.
Okay.